In this video, we are finally going to get to the definition that we've been working toward all semester. We're going to finally talk about rings. So the first thing we're going to do is review the number systems that we looked at in Investigation 6. And to be honest, in all the investigations before this, we're going to look at the properties from all of our number systems and see the ones that they have in common. Those are going to give us the axioms for the definition of rings, and then we're going to prove a theorem about rings. So let's look at all the number systems that we've been working on this semester. The first one we looked at, of course, was the integers. We looked at the even integers. Those were special because they didn't have a multiplicative identity. We looked at the congruence classes modulo n. We called those Zn. The rational numbers, we looked at those. The real numbers, we looked at complex numbers. Those were the first ones, well, actually, along with Zn, that we couldn't apply the order axioms to. And then the matrices over the real numbers, those were the first ones we looked at that didn't have a commutative multiplication. And then the weirdest one probably we looked at was the power set of a set with n elements, Pn. So these are very different number systems, and actually if we looked at the power set, those didn't even have numbers. Those elements had sets as elements. But it turned out they did have a lot of properties in common, and those are the properties that are going to give us the definition of a ring. So here were the common properties. Each of those number systems had two binary operations, which we called plus and multiplication, addition and multiplication. We noted that in all of those examples, addition was commutative, and multiplication was sometimes commutative, sometimes not commutative. Addition and multiplication were both associative for all the examples. In every example, the additive identity existed, but not always true that the multiplicative identity existed. Sometimes those exist, sometimes they didn't. Every element had an additive inverse for all of our examples, but not all elements had a multiplicative inverse. And that was even true even if we had a multiplicative identity. All the examples satisfied the distributive property. And so what we're going to do is we're going to take all of those statements, and those are the properties that define rings. So a ring is a set R along with two binary operations, which we call addition and multiplication, such that the following are satisfied. Addition and multiplication both have the associative property. Addition has the commutative property, not multiplication necessarily. There exists an additive identity in R, which we usually denote by 0 sub R, but of course we will only be able to do that once we prove that the additive identity is unique. But we'll get there. So for every element R in our ring, we have R plus 0R equals R. And we don't need to say this, but I want to make sure that we know that when we add 0 plus R in the other direction, we also get R. Every element of R has an additive inverse, which means that for every element little r, there is some s in R, such that R plus s equals 0. And also the other direction, s plus r equals 0. And once we prove that the additive inverse is unique, which we will do, which you will do in the in-class activities, we will write the additive inverse of R as negative R. The distributive property holds. Now we got to be careful about the distributive property. One thing about rings is that we don't necessarily have the commutative property for multiplication. So there's actually going to be two forms of the distributive property. One form, well, in all the cases, we're going to look at three elements of the ring, R, S, and T. The first version of the distributive property is going to look like R times S plus T, where we're multiplying R on the left and S plus T on the right. And then that's going to equal R times S plus R times T. Notice that R is on the left of all the things, both on the left side of the equation and the right side of the equation. But we're also going to have a distributive property when the R is on the right and the S plus T is on the left. So when we have that, we have S plus T times R equals S times R plus T times R. And then notice there the S and T are always on the left and the R is always on the right. And that is how the distributive property is going to work for rings that don't have a commutative multiplication. All right, so in class, you're going to prove two important properties about a given ring. You're first going to prove that there's exactly one additive identity in R, and don't panic, it's going to be exactly like it was back in the integer days. And we're going to prove that each element of R has precisely one additive inverse. So if we happen to have two elements R and S with R plus S equals 0, we can immediately conclude that S is equal to negative R. Actually, we can equally conclude that R is equal to negative S. Yeah. All right, so here's the theorem that we're going to prove. If R is a ring and X is an element of that ring, then negative X is equal to X. Now, before we get into the details of the proof, which actually is not going to be too bad once we know what we're supposed to be doing, we got to really clarify what negative X means. Each of those negatives means we're taking an additive inverse. An additive inverse means we add it to something to get 0. So each negative sign indicates an additive inverse, which means that negative X is going to be the additive inverse of negative X, and negative X is going to be the additive inverse of X. But what negative X means is that when whatever it is, when we add it to negative X, we should get 0. So in order to prove that X is the additive inverse of negative X, which is what we're proving, we need to prove that when we add X to negative X, we get 0. So we know negative X is the additive inverse of X. By the definition of additive inverse, that means that when we add it to X, we get 0. So X plus negative X equals 0. But if we look at that from another perspective, it says when we add X to negative X, we also get 0, which means that X is the additive inverse of negative X. So since X is the additive inverse of negative X, that means X is equal to negative X. All right, so now go ahead and try your hand at some of the proofs on our in-class activities. The name of the file is Elementary Ring Properties.